In this video, we will finish up our discussion of Taylor polynomials and their associated remainder estimate. So to begin, for the function square root x, let's find the Taylor polynomial t sub 2 centered at a equals 4. Once we have that Taylor polynomial, we will approximate the remainder on the given interval. So to begin, since it's centered at 4, t sub 2 of x is going to be equal to f of 4 plus f prime 4 times x minus 4 plus f double prime of 4 divided by 2 factorial, which is 2, multiplied by x minus 4 squared. And I'm going to leave a little bit of space to fill in the desired values. What we need to do at this point is calculate a few derivatives. So f of x is the square root of x. And in terms of differentiation, it's maybe convenient to rewrite this as 1/2. Then using the power rule, f prime of x is 1/2 x to the minus 1/2. F double prime is minus 1/4 x to the minus 3/2. And for future use, let's just know f triple prime is equal to 3/8 x to the minus 5/2. What we need to do at this point is determine 3 values, the first of which is f of 4. So f of 4 is the square root of 4, which is 2. The next value we need is f prime of 4. So f prime of 4 is equal to 1 over, and remember, raising to the 1/2 power is equivalent to dividing by the square root. So 2 square root of 4, which is 1/4. So plus 1/4 x minus 4. And then lastly, here to get the Taylor polynomial, note f double prime of 4 is going to be minus 1/4, and raising to the minus 3/2 is equivalent to dividing by 4 raised to the 3/2. And this is going to be equal to minus 1/32. And notice in our formula for the Taylor polynomial, we're dividing by 2, so we'll be subtracting 1 over 2 times 32, so 1 over 64 x minus 4 squared. And this would be the degree 2 Taylor polynomial for the function square root of x centered at 4. So let's now estimate the accuracy of the remainder on the interval from 4 to 4.2. And recall that the remainder estimate, r sub 2 of x, is bounded above an absolute value by m divided by n plus 1 factorial, so that'd be 3 factorial, multiplied by the absolute value of x minus a, so x minus 4 cubed. So we need to really do 2 things here. First, let's take care of the easier one. We need to determine how big can the absolute value of x minus 4 be on the interval. So if we're on the interval from 4 to 4.2, how far can you be away from 4? And the answer is you can be 0.2. So bounding above, this would become 0.2 cubed. The other thing we need to determine is the value of m. And recall that for the value of m, what we need to do is think about how big can the absolute value of the third derivative be on that interval. Well, if we look at our third derivative, which is 3/8 times 1 over x to the 5/2. As we go from 4 to 4.2, what's in the bottom is going to be getting bigger. So the important observation to make is that this is a decreasing function. And if we want to make a decreasing function as big as possible, what we need to do is plug in the smallest value. So f triple prime of x, that third derivative, is going to be less than or equal to f triple prime of 4. And this is specifically on the interval from 4 to 4.2. So if we plug in 4, we're going to have 3 over 8 times 4 to the 5/2. which is equal to 3 over 256, which is our value of m. So this becomes 3 over 3 factorial, which is 6, multiplied by 256, which if you plug into a calculator is approximately equal to 0.00015,625. And seeing this initial 0.0000, this is a pretty dang good approximation on the interval. Once again, an observation, the most difficult part of these remainder estimate problems are typically finding the value of m, which goes back to looking at the given derivative. Here, the third derivative, it's decreasing, so it will assume its largest value at the left-hand endpoint of the interval. Let's wrap up with another similar example. This time for the cube root of x, let's find the Taylor polynomial of degree 2, but now centered at a equals 8, and then estimate the accuracy of this approximation from 7 to 9. So t sub 2 of x will take on the form f of 8 plus f prime of 8 times x minus 8 plus f double prime of 8 divided by 2 factorial times x minus 8 squared. So once again, we need to find three numbers. The function evaluated at 8, f prime at 8, f double prime at 8. So let's do a few derivative calculations. So the cube root of x can slightly more conveniently be expressed as x raised to the 1/3 power. Then the power rule allows us to differentiate very conveniently. So 1/3 x to the minus 2/3. The second derivative is minus 2/9 x to the minus 5/3. And for future use, the third derivative will be equal to 10 over 27. That would be the minus 2/9 times minus 5/3. And then the new power is one less, so x to the minus 8/3. So let's do a couple quick evaluations. If we plug in 8, we have the cube root of 8, which is 2. So that gives us the first term in the degree 2 Taylor polynomial. F prime of 8 is equal to 1 over 3 multiplied by 8 raised to the positive 2/3 power, which is equal to 1/12, because we think 8 to the 2/3 would be the cube root of 8 squared, which is 4, times 3 gives us the 1/12. And lastly, for f double prime of 8, this is equal to minus 2 over 9 times 8 raised to the 5/3 power, which is equal to minus 2 divided by 288, which you can get conveniently by just plugging it into a calculator. And in the formula for the degree 2 Taylor polynomial, we're dividing this by 2, so the 2's cancel, and what we will end up with is subtracting 1 over 288 once we've made that cancellation with the 2's. So this gives us the degree 2 Taylor polynomial. And what remains is to estimate the accuracy of this approximation. So in order to estimate the approximation, what we need to do is look at that remainder term. So r sub 2 of x, the remainder for t sub 2, is bounded above, similar to before, m over 3 factorial times the absolute value of x minus 8 cubed, where we're thinking on our interval from 7 to 9, how big can m be, and how big can the absolute value of x minus 8 be? So let's start off maybe with the easier one. Looking at our interval going from 7 to 9, the absolute value of x minus 8 measures how far you can be away from 8. 7 and 9 are both 1 unit away, and that's as far as you can be. So that will be bounded above by 1 cubed, which is simply 1. Now for the m value, we need to think how big can the third derivative be on this interval. And the typical thing to think about is looking at our third derivative function. Will that be increasing or possibly decreasing? If it is, we can plug in one of the endpoints. Looking at the form of the function we have, as x increases, the bottom is getting bigger, which gives us something smaller. So f triple prime is once again decreasing. So if I want to make that third derivative as big as possible, what we should plug into it is the left-hand endpoint, 7. So the third derivative is less than or equal to the third derivative evaluated at 7. So in this case, that would be 10 over 27 multiplied by 1 over 7 raised to the 8/3 power. And it's not the most convenient quantity. Plugging into a calculator, it's approximately equal to 0.0021, and this is playing the role of our value of m. Plugging into our remainder estimate, we have 0.0021, divide it by 3 factorial, which is 6, multiplied by 1 cubed, which is 1, and this is 0.0004. And even though our interval from 7 to 9 is quite large, we see that the approximation is still quite good.